but for clarity's sake and for easy comprehension, I will use a kind of geometric approach.
Okay.
In that particular case, we'll look at these two figures. What is the usual XY axis? Here is 0. This is R cross R. Then here, assuming that here is the number A, and here is the number B, both are not negative. Then let this represent the graph of the function f of x equals x raised to the power b minus 1. B minus 1, where p is as indicated in the hypothesis. Then, in this particular case, I'll look at this picture. If we consider this, we'll observe that to see this. There are two areas depicted in the diagram. One is the area above the curve, and the other one is the area under the curve. The entire area under the curve, which are denoted by A1, and the area above the curve, which are denoted by A2. Interestingly, there is another area we can still observe, and that area is the area of the rectangle. If you look at that, then it's nothing but what? A times B, that is length times the width. But you observe that area under the curve is with the portion in blue more than the area above the curve. Yes. And this means that if we sum the area under the curve and the area above the curve, then we shall get an area that is bigger or equal to the area of the rectangle. Yes. Still representing f of x equals x raised to the power p minus 1. In this case, we find that we have something like this. This is the area under the curve, and this one goes this way. We can have this. See the area of this rectangle, the area above the curve. Apart from this rectangle, you see that something, this piece is also added to the area above the curve. So if I label the area under the curve A1, and that above the curve A2. A2, in fact, A2 is not just this portion. A2 is the whole. A2 is the whole area above the curve. I call this one fig 1, and here I have fig what? Fig 2. It is easy to see from fig 1 and fig 2 that A times B, that's the area of this rectangle. Area of the rectangle is less or equal to A1 plus what? A2. I'll call here, say, start. It's less than or equal to A1 plus A2. Here, this now I'm calling f of x, I can still call it what? Y. Let me even use the notation. Y equals x raised to 4y. I think I'm doing it for a purpose. So, from there, but what is A1? In either this or in both cases, in both figures, observe that irrespective of the figures, observe that A1 is equal to the integral from 0 to a of y dx, which is equal to the integral from 0 to a of x raised to power b minus 1 dx. And this, if evaluated, will give us a raised to power p over p. Over p. That's what we'll get. And let me do something here. And observe also, okay, observe further that y equals x raised to power p minus 1 is even equivalent to what? X or y raised to power q minus 1 equals x.
Okay. Yeah.
Using the fact that what? Using the fact that that 1 over p plus 1 over q is equal to 1.
Yeah.
Huh? Of course, this is gotten. You can expatiate. The most important thing is to show that from here, y equals x raised to power 1 p minus 1 means that x is equal to y raised to power 1 over p minus 1. So our ability to show that 1 over p minus 1 over p minus 1 is equal to q minus 1 does the job.
Okay.
Just to show that 1 over p minus 1 is equal to q minus 1. And that will give us the required. Therefore, A2 is equal to the integral from 0 to b of x dy. X dy, A2, the area above the curve, is the integral from 0 to b of what? X dy. And this is equal to the integral from 0 to b of y raised to power q minus 1 dy. And that will give us nothing but b raised to power q over q. B raised to power q over q.
Yeah.
AB is less or equal to A1 plus what? A2, which is equal to A raised to power p over p for A1 plus what? B raised to power p over what? Over q. And this completes the proof of that inequality. The inequality AB less or equal to A raised to power p over p plus B raised to power p over q is usually referred to as the Young's inequality. The Young's inequality. The Young's inequality. Okay. us to look at the proposition. Proposition 3. Here I'll take, we'll let P, Q be in 1 plus infinity, PQ in 1 plus infinity, with 1 over P plus 1 over Q equal to 1. If we make that assumption, we'll let n equals 1 to infinity, and Bn n equals 1 to infinity be sequences in, let me say, f equals c or r, such that summation n equals 1 to infinity, absolute value of n raised to power b is less or equal to 1. And the summation n equals 1 to infinity, absolute value of bn raised to power q is less or equal to 1. Then we can conclude that summation n equals 1 to infinity of absolute value of an bn is less or equal to 1. We can conclude this. The proof is simple. Very. The proof is simple and can compute. Given P, Q, n equals 1 to infinity, Bn n equals 1 to infinity, as in the hypothesis. In the hypothesis, when I talk about hypothesis, as in the what? In the proposition. If we're given that all these are what? Satisfied, then we obtain for all n in the set of natural numbers that absolute value of an bn, which we know is absolute value of an, absolute value of bn, is less or equal to absolute value of an to power p over p plus absolute value of bn to power q over what? Over q. Using the using proposition 2. Using proposition 2. So what this means? What does this mean? This means therefore, for any k and pk in the set of natural numbers, we have that summation n equals 1 to k of absolute value of an bn will be less than or equal to summation n equals 1 to k of what? Absolute value of an to power p over p plus absolute value of bn to power q over what? Over q. And this is nothing but summation n equals 1 to k, absolute value of an to power p all over p plus summation n equals 1 to k, absolute value of bn to power q all over q. All over q. There's the reason why I'm passing through this k before getting it completed. That is before allowing k to go to infinity. The reason is this: for you to see that all these things we are doing for series, for infinite series, also goes for what? For k.
Okay.
That is, if you have a finite number of terms, you can equally get the same result for the finite number of times. Assume that in the sense that if I assume that this goes from 1 to k, and that this is satisfied, also from 1 to k this is satisfied, then from 1 to k this will also be what? Satisfied. Or another way to view it is you may complete it for up to infinity. Then to get at the wholes for k, you may assume that what for n equals 1 to k, an is non-zero, and not all of them are zero. But from k plus 1 onwards, all of them will be what? Zero. In that case, when you partition the sum, you sum from n equals 1 to k, and then from k plus 1 to infinity. Then k plus 1 to infinity, being a countable sum of zeros, will give you 0. So you still get the required result for k. So all we are doing that also holds for what? For finite number of times. Good. So here now, if I now allow k to go to infinity, and I'm doing it, and the reason is clear that this is summable, this is summable, and that dominated by this is dominated by that, and this is a kind of a sequence of partial sums of non-negative terms, bounded, because therefore must also what? Combine. So that what I just said is deep. If you have a sequence of non-negative terms, and you have that the sequence of partial sums is bounded. In fact, what requires bounded above the series what? Watch here. What is Sn plus 1? Sn plus 1 will be what? A1 plus what? An plus what? An plus 1.
Yes.
Then if I do Sn plus 1 minus Sn plus 1 minus Sn, I will get what? An plus 1. And since this is a non-negative, sequence of non-negative terms, it means that this is greater or equal to 0. And this being greater or equal to 0 means that Sn is less or equal to Sn plus 1 for all n. Meaning that the sequence of partial sum is monotone increasing, bounded above, and therefore converges. Again, here, just mentioned it. And I need to throw light on that. So we have to be very careful with dealing with when we are dealing with all these things. All those elementary things are very important. Very, very important. Nothing should be jumped. Everything must be what? Must be taken proper care of. In the sense that the learning must be what? Total. There should be no hand waving. There should be no jumping of things. And I always say this, as you're going through anything that is not clear to you, stop there. Don't move further until that thing gets clear. If it doesn't get clear, don't move further. Make sure that you clear grounds before you continue. Because what I've noticed that some people, if they are studying some concepts, once they get to a place that is not all that clear, they will jump. They may even jump the entire chapter. You forget that the thing is built in a way that what? It feels progressively. The higher chapter has the lower one as a prerequisite. So if you don't understand what is done in the earlier chapter, you cannot follow in the other chapter. It's a sequence of partial sum of this series. This is convergent, and this is also a sequence of partial sum of this series that is called. So this is convergent, and for that reason, it means that this is bounded. Being bounded bounds this as a sequence of partial sum of what? Of this series. And therefore that tells me that this series is what? Convergent. And therefore I can pass limit.
Okay, so that's how you take limit.
You see now?
Yes.
The sequence of partial sum, this sequence of partial sum is what? Bounded. And it's a sequence of partial sum of what? Series of non-negative terms, because you have absolute value. Therefore it's convergent. Are you with me?
So it's the convergence that allows
that take limit as k goes to infinity. That if you are not sure that it's convergent, you can talk about limit.
Okay.
So when we do all those things, it's as if to say it's not making that there's no meaning. There are a lot of hidden meanings in all we are doing. So let me now remove the other.
Then, Prof, in this case, this one that is aside, you show that you're able to show that the sequence of partial sum is monotone.
That's actually
Increasing.
that's actually what it would be.
Okay, monotone. Okay, and then this is monotone increasing.
Every monotone increasing sequence bounded
Above
above
converges.
converges.
Then what of the series? Because the partial sum converges, series converges.
The convergence of the partial sum
Yeah.
is equivalent to the convergence of the series.
Okay.
A series is convergent if and only the sequence of partial sum converges.
Okay.
And whatever the sequence of partial sum goes to is the series.
Okay.
You get what I'm talking about? If the sequence of partial sum goes to x star, if Sn, the sequence of partial sum goes to x star, then S star is equal to summation n equals 1 to infinity of an.
Yes.
That's it.
Yes.
We said a series is convergent if
And only if the sequence of partial sum is convergent.
convergent.
That's it. Okay. So these are the things. In fact, let me tell you something. Even this thing we are doing, I think we are jumping the gun. Yes. That real analysis is very important. It's very important. And that is what I think we should. Let us get this to a particular level. The real thing to do is to what? Give a thorough lecture on classical analysis, real and classical analysis.
Yes, that's the next one.
Cover the ground,
Yes.
and that will be beneficial to so many, especially those that are still coming up.
Yes.
This will help them a lot. We'll give a thorough lecture on that particular thing. Then before we come into building these blocks.
Yes.
N equals 1 to k. Absolute value of a n, bn, absolute value of a n, bn is less or equal to summation n equals 1 to k. Absolute value of a n to the power p all over p plus summation n equals 1 to k. Absolute value of bn to the power q all over what q. And this is as k tends to infinity, we obtain that. I can do this because of the explanation I've given. You understand? This is a sequence of partial sum of a certain series. This is a sequence of partial sum of a series we know is convergent. And this is a sequence of partial sum of a sequence we know is convergent. And therefore these two are bounded. That allows this to be what?
Bounded.
And for the fact that this is a sequence of partial sum of a non-negative, of a series of non-negative terms, bounded above. Therefore, the series is convergent. Hence, as k tends to, I can do that now. As k tends to infinity, we have that we obtain that summation n equals 1 to infinity, absolute value of a and bn is less than or equal to summation n equals 1 to infinity, absolute value of a n to the power p over p plus summation n equals 1 to infinity, absolute value of bn to the power q over what? Over q. This is still less than or equal to 1 over q plus what? 1 over q. Because we are giving that this sum is less than or equal to 1. And this one is less than or equal to 1. And this is equal to what? Equal to 1. So what we've got is that summation n equals 1 to infinity, absolute value of a and bn is less than or equal to 1. So what does that mean? That completes the proof again. Because what it means is that whenever you have a series, a sequence of real numbers, a sequence of complex numbers, so that this series is less or equal to 1, and this one is less or equal to 1, then this particular thing will be less or equal to 1. That's what I said.